exercise of the chapter wave optics. Okay, come to the question 1. Monochromatic light has wavelength 589 nanometer. So lambda is given 589 nanometer. 1 nanometer is 10 power minus 9 meter. Is incident from air on a water surface. What are the wavelength, frequency, and speed of the reflected, refracted, and refracted light? Refractive index of water is 1.433. So here, so this water surface, light is incident, normal, reflected light, and refracted light. So the first case, when you take the reflected light is reflected to the same medium. As it is same medium, there is no change for any of these quantities. Lambda will be same, 589 nanometer. Then speed will be C is equal to 3 into 10 power 8 meter per second. And frequency you can calculate. Frequency is equal to C by lambda. Now, take the case of refracted light. For refracted light, these quantities will change. So what happens to wavelength? Lambda dash is equal to lambda by n. That will be the change in wavelength. Lambda dash is equal to lambda by n. And what happens to speed? Speed v is equal to c by n. All these equations you have studied. C by n. And frequency, during refraction there is no change in frequency, so frequency remains same, mu dash is equal to nu. So in this way you will get the answers. Now next, question 2. What is the shape of wavefront in each of the following cases? A light diverging from a point source. So the point source, wavefront will be spherical. Spherical wavefront. Then light emerging out of a convex lens when a point object is placed at the focus. When the object is at the focus, image is at infinity, which means a parallel beam is produced. Therefore, the wavefront will be plane wavefront. You get a plane wavefront. And a portion of wavefront of light from a distant star intercepted by Earth from distant objects, again you will get a plane wavefront. Okay, that's about question 2. Now come to question 3. The refractive index of class 1.5. What is the speed of light in class? Speed of light in vacuum is given. Direct calculation only. Use the formula n is equal to c by v. Find the value of v, n and c are given. Then is the speed of light in glass independent of color? If not, which of the two colors, red and violet, travels slower in a glass prism? Okay, we know that glass is a dispersive medium, so speed depends on wavelength or color. Then which of the two colors, red and violet, travel slower in a medium? Then Yeah, you know that almost a refractive index we can say, not exactly, then also inversely proportional to wavelength. Therefore, we can say NV greater than NR. NV greater than NR. Okay, because red has more wavelength. Then we can have the relation again N is equal to C by V, or V is equal to C by N. Now you see violet has more refractive index. Therefore, we can say violet light will move slowly. Violet light will move slowly in a medium. Okay, now that's about question 3. Now come to question 4. Young's double slit experiment. Slits are separated by 0.28 millimeter. So that means D is given. Slit separation 0.28 into 10 power minus 3 meter. Then the screen is at 1.4 meter away. 1.4 meter. The distance between central bright fringe and the fourth bright fringe is measured to be 1.2 centimeter. So y4 is equal to 1.2 into 10 power minus 2 meter. Determine the wavelength of light. Directly use the formula. Y4 is equal to y4 is equal to 4 lambda d by d. You will get the answer. So from this, you have to find the value of cross multiply the equation and find the value of lambda. Now, next, question 5. Next double slit experiment. Using monochromatic light of wavelength lambda, the intensity of light at a point on the screen where path difference is lambda is k units. What is the intensity of light for a path difference? Lambda by 3. Okay. Now, we have to see the situation carefully there. So when path difference is lambda, okay, path difference x is equal to lambda. For one complete wave, the phase difference will be 2 pi, 360 degree, one complete wave, one crust and one trough, like that you get it. Okay, so in such a situation, so substitute in the formula, we can have intensity formula E is equal to 4 I naught cos square pi by 2, or 2 pi by 2 is equal to, you will get the answer cos 180 minus 1 minus 1 square 1, so you will get the answer 4 I naught. And this 4 I naught intensity for a path difference lambda or difference 2 pi, you are asked to take as k. Now, so that is the first case. Come to the second case. Second case, path difference x is equal to lambda by 3, which means phase difference phi is equal to phase difference phi is equal to 2 pi by 3. pi by 2 pi divided by 2 into 3 is equal to, so here you 2 and 2 cancel, pi by 60, cos 60 is 1 by 2, cos square 60 is 1 by 4, therefore you will get the answer I know. So now 4 I note is k. So how much is I note? I note is equal to k by 4. Therefore we can say intensity I dash for a path difference lambda by 3 is equal to k by 4 is the intensity. Okay. Now question 6. Two wavelengths can take as lambda 1 and lambda 2. Lambda 1 is equal to 650 nanometer. You have to convert into meter. And 2 is equal to 520. 3 lambda d by b. Okay, so you cannot solve the problem because small d and capital D are not given in the question. But you will get the question in examination with the enough data that time you have to solve it. Now see the second part of the question. What is the least distance from the central maximum where the bright fringes due to both the wavelengths coincide? So bright fringes due to both the wavelengths coincide means their wavelengths are different. So the bright fringes of same value of n cannot coincide there. So least there will be a difference of n and n minus 1 like that. Least difference. Now you see here lambda 1 is bigger wavelength compared to lambda 2. And y formula, yn is equal to m lambda d by d. So at least minimum there is a difference of 1. If the large wavelength it is n, sorry, if the large wavelength if it is n, then you can see there the small wavelength should be n plus 1, because when wavelength increases y value also increases. Okay, anyway, now we can take like this. Suppose you have n lambda 2, nth wavelength of lambda 2, which is a small wavelength, coincide with the n minus 1 to wavelength of the larger one, that is lambda 1, n minus 1 to wavelength of the larger one. So at least the least difference we can take 1 when they coincide. So from this equation, okay, we can find the value of n. Substitute the value of lambda 1 and lambda 2 and find the value of n. Once you get the value of n, then you can find the value of y. Y is equal to one of the wavelengths we can use. For example, suppose you use lambda 2, then n lambda d by d. Value of y you can calculate. Okay. Now, next question 7. In a double slit experiment, the angular width of a fridge is found to be 0.2 degree. Angular width of a fridge. Angular width formula, theta is equal to beta divided by d is equal to lambda divided by small d. This is the formula. The screen is 1 meter away. The wavelength of light used is 600 nanometer. What will be the angular width of the fridge if the entire experimental apparatus is immersed in water? So if the entire apparatus immersed in water means, then you can see lambda 2 is equal to lambda 1 by n. The wavelength of the change in wavelength, where n is the refractive index of water. Okay. Now here, all this will be same. So you can take the ratio theta 2 divided by theta 1. Use the first formula. Theta 2 divided by theta 1 is equal to lambda 2 divided by lambda 1 is equal to, substitute the relation between 1 and lambda 2, you will get 1 by n. From there, you can find the value of theta 2. Theta 2 is equal to theta 1 divided by n. You will get the answer. Answer will be in degree. Okay. Then, what is the Bruce angle for air to glass transition? Refractive index is 1.5. Use the formula refractive index boosted your law you can use. Mu is equal to tan I. Mu is equal to tan I. You can the value of I. Then question 10. Light of wavelength 5000 angstrom falls on a plane reflecting surface. Wavelength and frequencies of reflected light. Reflection means it is towards the same medium. So wavelength will be same 5000 angstrom. There is no change. 5000 angstrom. Then speed will be c is equal to, can take it as air, so 3 into 10 power 8 meter per second. Then frequency is equal to c by lambda. Then for what angle of incidence is the reflected ray normal to the incident ray? So angle between reflected ray and incident ray is 90 degree. That means angle of incidence is equal to 45 degree. Then next, question 10. Estimate the distance for which ray of TC is a good approximation for an aperture of 4 millimeter. Aperture size A is given 4 millimeter. Convert 4 into 10 power minus 3 meter. Then wavelength of light lambda is equal to 400 into 10 power minus 9 meter. Then I told you ray of TC is good approximation means is something related to Fresnel distance. Formula Z is equal to a square by lambda. Okay. So that the distance is Z you can calculate. So substitute the value of A and lambda and find the value of Z. Now, next, question 11 is not required for you. Question 12. Explain how corpuscular theory predicts the speed of light in a medium, say water, to be greater than the speed of light in vacuum. Actually it is opposite. Okay. But according to corpuscular theory, it happens. How it happens? That is the question. So we can explain with the help of a diagram. So see here a surface. Okay, say water. Then light is incident. You can have the normal. Then refracted light into water. Here you can take in air, you can take velocity v1, and in water you can take velocity v2. Now this is angle of incidence, angle of refraction. Now according to correlative theory, see this incident velocity you can resolve into components. So like this, you can have horizontal component and vertical component. This will be v1 sin I, and this will be v1 cos I. The same way here v2 is the velocity. Okay, so velocity v2 you can resolve into particular components like this. So here you have v2 cos r, and horizontal component is v2 sin r. Now, according to corpuscular theory, the change will occur in the case of vertical components, only in the case of vertical components. So components are equal corpuscular. So then you can write v1 sin I is equal to v2 sin r. v1 sin I is equal to v2 sin r, or v2 by v1 is equal to sin I divided by sin r. Sin I divided by sin r. Now you see that angle I greater than angle r. Therefore, v2 greater than v1. So where is more speed then? You have more speed water. This is why in water the speed is high according to corpuscular theory. But you know, as this prediction is wrong, you have to use wave optics to get a correct idea, which is in agreement with the experiment. Next, question 30. If learned Huygens principle leads to the laws of reflection and refraction, use the same to use directly. Use the same principle to deduce directly object whose distance from the mirror is equal to the object distance from the mirror. What is that? Question is simple only. Using Huygens principle, you have to show that object distance and image distance are equal in the case of a plane mirror. That is the question actually. Anyhow, that's a geometry. You can try for a geometrical proof. Okay. Now, we can take a plane mirror. Here and have the plane mirror. Then a wavefront, okay, is interacting with the plane mirror here, a wavefront. So I'll just draw that wavefront like this. A spherical wavefront, okay. Spherical wavefront AB. This is mirror A. So what happens to this spherical wavefront AB? After reaching this point here, what happens? It reflects. When it reflects, what happens at a particular time? Imagine it travels for a distance r. So here, after falling on the mirror, it reflects back towards this point at a time t and for a distance r. Now you just imagine the mirror is not present there. When the mirror is not present, through the same medium, this wavefront AB will travel downwards. And at time t, it will reach here. Again, this point A dash B dash. So what happens? At time t equal to 0, the wavefront AB will reach at the mirror. In the absence of mirror, suppose mirror is not there, then AB will reach the point A dash B dash for a time t, and it travels for a in through air. In the presence of mirror, what happens? AB will reflect back from there. It will travel through the same distance r through air for a time t, and will reach here. Okay, that reflected wavefront I can mark as A dash B dash, A double dash and B double dash. Okay, this is a situation in the presence of mirror. From time t equal to 0, it reaches at the position A dash B dash. In the presence of mirror, wavefront AB will reflect back and will travel the same distance r through air for the time t. Now, in such a situation, now take the case the mirror is present. When the mirror is present, what will happen? The wavefront AB will reflect back, and what is traveling towards here with the same speed? Its image is traveling. Image of AB is traveling. So A dash B dash can be considered as the image, while A double dash B double dash is the reflected wavefront. So in such a situation, you can see from the symmetry of the diagram, we can say object distance r is equal to image distance r dash. Okay, from the geometry, you have to draw a diagram like that. Then you have to claim from the geometry of the diagram, both these distances r and r dash are equal, because we know that A dash B dash can be considered as the image, and it travels with the same speed, same distance. In the absence of mirror, you will get the same wavefront AB at A dash B dash. So from the symmetry of the ray diagram, we can say object distance is equal to image distance. Okay. Then next question 14. Which would possibly influence the speed of light wave propagation? Okay, five factors are given there. Out of these five factors, on which of these factors, if any, does the speed of light in vacuum depend? Actually, no factors, none of them. Okay, and speed of light in a medium like a glass, water, etc. For that, the wavelength, it depends on the fourth factor, wavelength. Only on wavelength, no other factor. Then question 16. In double slit experiment using light of wavelength 600 nanometer, the angular width of a fringe formed on a distant screen is 0.1 degree. What is the spacing between two slits? Double slit experiment. Angular width theta is equal to lambda divided by d. Lambda is given, theta is given, so that you can find the value of d. So one thing you have to do, when you find the value of d, when you substitute the value, theta must be in radian. Okay. Do not substitute in degree. Degree you have to convert to radian when you substitute in the formula. Okay. Now question 17. Answer the following question. In a single slit diffraction experiment, the width of the slit is made double the original width. How does this affect the size and intensity of the central maximum? Okay, central maximum beta naught is equal to 2 lambda d by a. Now, question says that a becomes 2a. If a becomes 2a, a becomes 2a, then what happens? Beta naught dash becomes beta naught by 2, become half of the initial size. Then next, how does the okay, that's about the size of the central maximum. Now intensity of the central maximum. What happens to the intensity of the central maximum? So here the size of the central maximum becomes half, means you can see intensity. What happens to the intensity? Then the intensity becomes, okay, there is an inverse square law relation actually. So whatever intensity you are getting initially, it will get in 1/4 of the part now, like that. Okay, so how it happens, we can say area is equal to pi r square. Area is equal to pi r square, you will get. So here what happens, you can see the slit width a becomes double. When it a becomes double, then you can see here beta naught becomes half. Okay, the size of the central maximum becomes half. Size of the central maximum becomes half, means you can see its area becomes half of the initial value. The area becomes half of the initial value. As the area becomes half of the initial value, then according to uh, intensity, uh, and area relation, okay, we can see uh, it becomes around 1 by sorry, it becomes around 4 times. We can see intensity is increased by 4 times. Actually, that relation you are not studying. Okay, there is in photometry that we have taken I is equal to a square. Remember that I is equal to intensity is equal to area, sorry, amplitude square. So there is a relation connecting this area and amplitude square. Using that relation, okay, detailed formula and all you are not studying. the intensity becomes 4 times. Okay. Now, next. In what way diffraction from each slit related to the interference pattern in a double slit experiment? Already we have seen in the theory, the interference pattern gets modulated. Gets modulated. Okay. Then next, when a tiny circular obstacle is placed at the path of light from a distant source, a bright spot is seen at the center of the shadow of the obstacle. Explain why. So here a beam of light you can take like this. An obstacle is placed, an opaque object. So what happens? Light will bend over. Bending of light means diffraction. Diffraction pattern will produce a central maximum here. And that central maximum is observed as the bright spot. So around the particle, a diffraction pattern is produced. Central maximum of that diffraction pattern will give a bright spot. Then next, two students are separated by a 7-meter partition wall in the room, 10-meter high. If both light and sound wave can bend around the obstacle, how is it that the students are unable to see each other even though they can converse easily? Okay, here the reason is wavelength lambda. Both light and sound waves can bend over the obstacles, but wavelength of sound is very large compared to wavelength of light. So sound waves can have more bending. Now sound waves can have more bending. So what happens is the sound can bend over the wall. But bending of light is limited. It cannot bend large amount. So then what happens? You cannot see each other, but you can hear the sound. Light cannot bend over the wall at all. Okay, because its wavelength is small. Now, next. Ray optics is based on the assumption that the light travels in a straight line. Diffraction effects observed and the light propagates through a small aperture slits around small obstacles disapprove this assumption. Yet the ray optics assumption is so commonly used in understanding location and several other properties of images of optical instrument. What is the justification? Okay, we know that the correct optics that we can use is the wave optics, which is applicable in all these cases. But for explaining optical instruments, telescope, microscope, like that, we have used ray optics. In last chapter only, we have studied the basics of telescope, microscope, etc. And what is the reason? That's the question. So the reason, in these instruments, okay, lens is there, and the lens acts as the slit. Already we have seen lens is not an ideal slit. Okay, as lens is not the ideal slit, so the diffraction, we do not consider much diffraction effect there. In such a situation, we can use ray optics. When diffraction effect is high, then only rigorously we need to apply wave optics. Here, this is not an ideal slit, lens is not an ideal slit, therefore we can use ray optics. Okay. Then, next, uh, this part I want to give a little more explanation for the part A. Okay. Here we have seen beta, the central maximum fringe width that is decreased by a factor 2. Okay, that means R becomes R by 2. When R becomes R by 2, R becomes R by 2, what happens to A? A becomes A by 4. Okay, A becomes A by 4. Area becomes 1 by 4. So then what happens? Initially there is a particular area for central maximum. Now it is only 1 by 4th area. So whatever light is present in this area, now we present in this 1 by 4th area. So area becomes 1 by 4th. So intensity becomes 4 times. Okay, area of the region becomes 1 by 4. So intensity, the density of light in that area becomes 4 times. Like that, you can give an explanation for the part A. Okay, let's continue. Now, we can have two towers, 18 two towers on the top of two hills are 40 kilometers apart. The line joining them passes 50 meters above the hill halfway between towers. What is the longest wavelength of radio waves which can be sent between the towers without appreciable diffraction effect? That last sentence you have to see very carefully, without appreciable diffraction effects. So we can draw a diagram. Okay, we have the first hill, then the second one, then the third one. Okay, so towers from this tower, the signal is sent. When the signal is sent, the signal will go like this. The signal will cut like this from the tower when it is sent. Okay, if it is going like this, what happens? Then the signal will be cut by the mountain in between. Okay, so the straight line distance we can take in this way, and this mountain is exactly in between. So, and from the straight line from the mountain, it is given that distance is 50 meters. So maximum how much spreading can be possible for the signal? A signal can have maximum spreading 50 meter maximum. If there is a spreading more than 50 meter, then the mountain in the center will block the signal. And this distance, total distance is 40 kilometer, and so this distance is 20 kilometer. When the signal travels 20 kilometer, maximum spreading is 50 meter possible, maximum. So what to do to find the wavelength? So for a 20 kilometer distance, spreading 50 kilometer. For a given distance, for a particular spreading of light. Okay, which topics you have studied? Again, that you have studied in Fresnel distance. For Fresnel distance, for a distance Z, maximum possible spreading is A, the size of the slit. So you got the formula Z is equal to A square by lambda. For a distance Z, you can take it as 20 kilometer. The maximum spreading A There you have studied as slit width. So Z is equal to A square by lambda. From this formula, substitute the value of A as 50, Z as 20 kilometer, and find the value of lambda. Now, next, question 19. A parallel beam of light of wavelength 550 nanometer, wavelength is given, 500 nanometer, falls on a narrow slit and the resulting diffraction pattern is observed on the screen 1 meter away, capital D. The first minimum is at a distance 2.5 millimeter. Okay, why? Find the width of the slit. So use the formula y1 is equal to first minimum. So y1 is equal to lambda d by a. Y1 is equal to lambda d by a. Substitute the values and find the value of slit width a. Then question 20. When a low-flying aircraft passes overhead, we sometimes notice a slight shaking of the picture on our TV screen. Suggest a possible explanation. Okay. So here, low-flying aircraft, okay, when it is passing, there will be a small uh, shake in the picture. What is the reason? Okay, so we are getting signal from satellite, right? So signals you will get from satellite. So from there, when the signal reaches from the satellite, you have two possibilities are there. One, the signal that falls on the aircraft and gets reflected towards your antenna. Okay. Now, another possibility you can see the signal can be directly reached towards your antenna. So both the signals are there. Then in such a situation, when they reach, what happens? Whenever there is a reflection, then reflection will make a phase change 180 degree. 180 degree phase change will be there. So in such a situation, whenever there is a 180 degree phase change, and here the direct signal and the reflected signal will interfere. There will be interference will be there. So when there is an interference, what will happen? See that they are 180 degree out of phase. So momentarily they cancel each other due to interference. As they cancel each other momentarily, okay, you will lose the signal for a moment. That is the reason you will see slight shaking of the picture. So what happens? Signal will be reflected from the aircraft and it undergoes 180 degree phase change. The direct signal and reflected signal destructively interfere so that for a moment the signal will be lost. That is the reason for the slight shaking of the picture on TV screen. That second. Part B. As you have learned in the text, the principle of linear superposition of wave displacement is basic to the understanding intensity distribution in diffraction and interference pattern. What is the justification? So what is the question? You have taken, okay, superposition y is equal to y1 plus y2. Y is equal to y1 plus y2. So it is not y1 square or y2 square or cube or anything. Higher powers we have not taken. But in certain circumstances, like a laser, the amplitude will be high. As amplitude is high, you cannot use this linear superposition y1 plus y2. Instead of that, in such a situation for high amplitudes, you will get squares, cubes, etc. Okay, so linear superposition is possible, not possible. So in this case, we deal with small amplitudes. We can use linear superposition. Okay. Question 21. In deriving single slit diffraction pattern, it was stated that the intensity is zero at angles n lambda by a. Moreover, n lambda by a corresponding to minimum. Justify this by suitably dividing the slit to bring out the cancellation. So, how you divide the slit to get cancellation? Already you have done in derivation. Your written slit can be divided into two equal parts, four equal parts, six equal parts, and you will get a cancellation. Okay, so just assume here the slit is divided into n equal parts, and the size of each part a dash is equal to a divided by n. A is the slit size. Okay, now we can take angular width sine theta is equal to sine theta n is equal to n lambda divided by a. You know, sine theta n is equal to n lambda divided by a. So for small angles sine theta you can approximate to theta. So you will get a theta n is equal to n lambda divided by a. Their value of a you can substitute. You will get n lambda divided by n a dash, n cancel. So you will get a theta n is equal to the angular width. Okay, the angular width theta n is equal to lambda divided by a dash, where a dash is the each part of the slit. Such parts together will bring out the cancellation. So angular width theta n is equal to lambda divided by a dash, where a dash is the each part of the slit, and such parts together will cancel each other to get a minimum.